Hey everyone, my name is Han Chen, and I'm a rising fourth-year undergraduate student at Chicago. Today, I'll present our work, CacheGen, KV cache compression and streaming for fast language model serving. This work was carried out by the University of Chicago, Microsoft, and Stanford University. A quick introduction to first author Yu Han. She's a rising fourth-year PhD at Chicago, advised by Junchen and Shan. Nowadays, large language model inferences are equipped with context. For example, in this ChatGPT session, the user first gives a document about Amazon 2023 annual report, and then asks this question: what generates the most operating income for Amazon in 2023? Although the model might not be trained on this specific document, it is able to give a very accurate answer due to the presence of this background information. These type of documents, since they give relevant information for the model to answer questions, we call them context from now on. Similar applications including retrieval augmented generation or RAG, and gaming agents with conversation histories all uses context to supplement their inference. However, processing long context can be very, very slow. So if you feed a document and a query to a Llama 70B model, what happens is this: it will first go through a phase called preview, which processes the context into an intermediate form that large language model can understand. And then you will go through a preview for the user query. Only after these steps, you can generate the answers one by one. And it is at least 9.5 seconds before the user gets any response in this case. So what does this lengthy preview do? So this lengthy preview actually produces something called a KV cache, which are two 3D tensors of shape, number of neural network layers, number of tokens, and number of channels. So tokens here means it's a unit in language processing, and it's slightly less than a word, and channels are hidden states of a neural network. Luckily, we can reuse these KV cache and reduce the preview delay. So this is the same example. You feed this through a large language model, and then you get KV cache, you get the response, and then a second question came asking what generates the most profit for Amazon in 2023. Since the context you use might be the same, you can just reuse the KV cache for the context. And then you can skip all these lengthy preview of the context, and user gets very satisfied. However, this is not the case in real life. KV cache might need to be transferred. And here's why it might need to be transferred. So first of all, volatile memories cannot hold all the KV cache. So this is the exact same scenario. You put the KV cache in GPU server number 1, and a bunch of other requests comes in. Since these requests, they occupy the DRAM as well, the KV cache will get evicted since the memory is limited. And then when the second request comes in, like what generates the most profit for Amazon in 2023, the KV cache is already not there. So you have to do preview again. Similar problem hold for CPU as well. So here's a memory comparison. So for A40 GPU, you can put 9 contexts of 16,000 tokens. And here is a breakdown of the size of the KV cache. And when the token number increases, the size also increases as well. Another case is that you can reuse KV cache across different servers. So suppose the first inference is directed to server number 1, and you did this prefill for Amazon annual report, and then a second request comes in and it's directed to server number 2. You want to reuse this KV cache, but you got to send it through a network link. So it might not be a really high bandwidth link like NVLink, and this potentially gives a networking challenge. So the goal of CacheGen looks like this. So you have this naive preview baseline that's taking 9.5 seconds. And you have this reusing original KV cache baseline. So if you're sending this KV cache through a network link of 3 gigabit per second, the transfer time is actually higher than the original preview time, and you don't want this to happen. So what CacheGen tries to do is you compress this KV cache, and then you can have a much lower transfer time with a little bit of decompression time. And this can be much, much faster than both baselines. So here's a demo of how CacheGen reduces the preview delay. So in this demo, on the right is just we give the CacheGen paper to the large language model. And on the left, we ask this question: what are the data sets used in the paper? So let's see how naive baselines perform. You can see here is just pre-feeding. It takes 7.16 seconds before any output is generated. And for CacheGen, we enable the optimization up there, and then we ask the same question. And now the answer is here. So it's a nice 2.7 seconds, much shorter than the original baseline. And the user will be more satisfied if you use these kind of applications. So here's how we do this. This is an end-to-end system overview. So you take the original KV cache and you compress them into compact bit streams and you put them into storage devices offline. When the context is needed, it's loaded into GPU first, and then we perform a GPU-based decompression to restore the original KV cache, and this can speed up the generation by a large amount. And today, the talk will mainly focus on the compression part. So the key insight in CacheGen is instead of moving the tensors, we move the bits. Prior methods, mainly in the machine learning community, they try to compress this KV cache to another tensor format because they want to increase the batch size in the GPU for faster decoding. But in CacheGen, since we're already sending through a network link, you can just compress into bitstream format, which is more natural for networks. And this can reduce the size by a large amount. Moreover, it is worth noting that these methods can work together with CacheGen, and we will discuss the result later. So the opportunity number one brought by encoding into bitstreams is this. KV cache of nearby tokens are similar. Here is a heat map of a specific layer in a key cache. So the y-axis is the channel and the x-axis is the tokens. And if the value is bigger, it's lighter. This might not be too clear. Let's zoom in a little bit. So as you can see here, the values are more similar if the tokens are more near. But if the tokens are more distant, the values are different. So what we do is we compress the delta with the nearby tokens instead of compressing the original value. Here's a demonstration of how we compress the delta. You take this key cache at layer J. You first separate them into token groups, each comprised of approximately 20 tokens. And then you set the first token in this group as an anchor token. For the later tokens, instead of compressing the original values, you compress the difference of these token value with the anchor token. And you do the same thing for all the groups, and this is what you'll get. As you can see here, the values are almost zeros, and this has lower variance and it's much easier to compress. Second thing is we design a better arithmetic coding scheme. So what arithmetic coding does, it takes a probability distribution of an input symbols and takes the input symbols and it compresses into bit streams. One very important property of this is that the more skewed the input distribution is, the smaller the bit stream will be. So an example of this would be if you have 90% symbol A and 10% symbol B in your data, it will have lower entropy. And after you compress them, it will be of smaller size than if you have, say, like 50% A and 50% B, since that distribution has higher entropy. So what CacheGen does is tries to decrease this entropy by smart grouping of the data. So this graph shows, so the y-axis is the bit per element, or you can think of it as like a representation of entropy, and there are different bars. So the blue bar is the very naive baseline, which is you take the key cache, and then you don't do anything at all. You just take the distribution of the whole elements in this key cache and you compress them as a whole. But for say if you group by token, it means for each token I you get distribution for the tensors with token index fixed at I, and then you do arithmetic encoding for each group with this fixed token index, and then you add them up for the size. So as you can see here, if you group by channel or layer, the size is smaller. So what CacheGen does is we ended up grouping by channel and layer in the same time, and this saves us some more size. So opportunity number 3 is that later layers can endure more loss. So this graph is like we apply the same amount of arrow to different layer groups. Some of them are like earlier layers, some of them are later layers. And as you can see here, if you apply the loss to earlier layers, the accuracy drops by a significant amount. But if you apply to later layers, it doesn't really matter. The rationale behind it is that if you apply the loss to earlier layers, the arrow will actually propagate through the neural network computation, and then it will cause the accuracy drop. But if you do it to later layers, the arrow doesn't propagate that much. And what CacheGen use is it applies more aggressive quantization to later layers. And so the overall compression workflow looks like this. You take the original KV cache, you apply delta encoding, you do smart arithmetic coding, and then you do this layer-wise quantization to get a compact bit string. So for decompression, you basically do the same thing in the inverse order. And since it is slow to decompress with arithmetic coding on CPU, we wrote a custom CUDA kernel to do this arithmetic coding, and we pipelined the transfer of KV cache with decompression. One thing worth noting here is that decompression cost is much, much slower than prefill. So this is an intuitive compression. The y-axis is the number of teraflops. It's like floating point operations. And as you can see here, decompression is almost invisible if you compare them visually. For our evaluation, we in this talk, we report on dataset long chat on accuracy, and the default network link is 3 gigabit per second. For system metrics, we report the size of KV caches in megabyte, and we also report TTFT. Think of it as time to first token or total prefill delay. So we first show up speed up with high accuracy. So in this graph, the x-axis is the size of the KV cache, and the y-axis is the accuracy. This is the quantization baseline of 8-bit, 4-bit, and 3-bit. And this is CacheGen. So when there is almost no accuracy drop, CacheGen saves 4.3 times the storage space. What about the actual time? So this is a quantization baseline, and here's the naive prefill baseline, and here is where CacheGen lies. It saves the astonishing 3.7 times delay compared with the 8-bit almost lossless quantization baselines. In this graph, we compare CacheGen with different methods under varying bandwidth. So prefill doesn't depend on network at all, so it's the same. Quantization, when the bandwidth increases, the delay decreases. And for CacheGen, they always outperforms quantization baselines. Notice that on the high bandwidth, CacheGen and quantization both have very, very low delay compared with prefill. But CacheGen, since it saves the storage size, you can put more KV cache in the same amount of storage disk, or you could save some cloud storage cost. So, but in these cases, the delay saving is not the main part of CacheGen benefit. So here is CacheGen's improvement on top of other methods. So H2O and LM-Lingual here are two popular token dropping mechanisms from the machine learning community. As you can see here, CacheGen reduces the size of KV cache on top of other methods as well. In conclusion, smartly loading KV cache can save prefill delay. CacheGen compresses KV cache into compact bit streams for efficient network transfer through custom KV codec. It reduces the size of KV cache by 4.3 times and the delay to load KV caches by 3.7 times. And this is a project that we're building at UChicago. It's called LM Cache, and it integrates CacheGen and some other papers. The demo we just showed was actually using this. So scan to give it a try if you're interested. And I'm looking forward to meeting you all at the conference.